In this lecture, we will cover the CFA Level 2 reading on portfolio concepts. This is a long reading, and each of these sections are fairly substantial. Fortunately, though, approximately 70% of this reading should be familiar between portfolio management at level 1 and equity at level 2. Many of the things that you will see here should look familiar. All right, first a few introductory remarks, and here essentially we have a bunch of questions which are listed in the curriculum. The point being that over the last few decades, there have been several relevant questions asked by portfolio managers. Those questions, or at least some of them, are shown here. What characteristics of a portfolio are important? How may we quantify them? How do we model risk? If we could know the distribution of asset returns, how would we select an optimal portfolio? How do we combine risky assets with risk-free assets? We can use historical data, but what are the limitations? What risk factors should we consider in addition to market risk? And in this reading, we are going to answer these questions. All right, let's start with section 2, mean variance analysis. I often start this segment by asking a very simple question. What does mean variance analysis mean? So here is one response. When we talk about mean variance portfolio theory, we are talking about the idea that the value of investment opportunities can be meaningfully measured in terms of mean return and variance of return. Putting it another way, when you are analyzing a particular portfolio, you can look at what is the mean return or the expected return, and then what is the risk. And in mean variance analysis, the measure of risk is variance. Ideally, for a given level of risk, you want the maximum return. You need to learn the assumptions behind mean variance analysis, and these assumptions are fairly straightforward. I'll read them with you and help you memorize them. The first assumption is that all investors are risk averse, which means that they prefer less risk given a certain level of return, and we saw this at level 1. So assumption 1, investors are risk averse. Assumption number 2, expected returns for all assets are known. Since this analysis is based on mean and variance, this is the mean return that we are talking about. So we are assuming that for all assets that we are analyzing, the mean return is known. Similarly, the variances are known, and the covariances between assets are also known. Then number 4, investors need only know the expected returns, variances, and covariances of returns to determine optimal portfolio. Implied in here is the fact that investors can ignore skewness, kurtosis, and other attributes of a distribution. So this is a major simplification. And finally, we assume that there are no transaction costs and no taxes. So make sure that you remember these 5 assumptions. They are mentioned in the learning objectives. All right, section 2, mean variance analysis, has several subsections. We'll first talk about the minimum variance frontier and related concepts. We will talk about 2 asset portfolios over here. Then we will talk about the 3 asset case. We'll talk about determining the minimum variance frontier for many assets. Then we'll talk about the relationship between the size of a portfolio and the diversification benefit. Then we'll talk about portfolio choice when we introduce a risk-free asset. In sections 1 through 4, we are only considering risky assets. Then we talk about the capital asset pricing model, and finally, we talk about mean variance portfolio choice rules. And this is a very introductory segment. This material is covered in more detail at level 3. All right. Minimum variance frontier and related concepts. I'll start this little segment by giving you a small question to do, and this will check how well you remember your level 1 material. You are constructing a portfolio with 2 assets. These are actually asset classes. So asset class 1 is large cap stocks, asset class 2 is government bonds. You are given the expected return, the variance, the correlation. What is the expected return of the portfolio and what is the variance of the portfolio given these weights? 70% in asset 1 and 30% of your money in asset 2. So these are the formulas from level 1 that I expect you to remember. The expected return of the portfolio is simply the weighted average. So in this context, we'll put 0.7 into the expected return, which is 15. And then weight 2 is 0.3 into the expected return, which is 5%. Fairly straightforward. On the next slide, I'll show you the actual number. And this is the formula that is a little harder to remember, but it is a formula that you have to remember. You used it at level 1, you are using it at level 2, and you will need it at level 3. So stare at it very carefully. We are calculating the variance. Once you have the variance, you can find the square root if you need the standard deviation. So just plug in the numbers. This is the correlation between the 2 assets, which is 0.5. Okay, when you plug in the numbers, what do you get? If we look at this table, it actually shows the portfolio expected return, variance, and standard deviation for different weights of asset 1 and asset 2. The weight that I asked you to use was right here, 70% in 1 and 30% in 2. So if you did your calculations right, the expected return is 12%, variance is 150.75. And then what this table is doing is just showing the return and variance numbers for a whole set of different weightages. If we plot this out, then this is what we get. On the x-axis, we have the variance of the portfolio. On the y-axis, we have the expected return of the portfolio. This point, which says 0%, refers to 0% invested in asset 1, which was our large cap stocks. Then the return is the return on bonds. All right. Then as you move in this direction, we are adding stocks to our portfolio. And notice a diversification benefit which happens. At roughly the same risk and perhaps a little less risk, you can actually increase your return. And as you keep going, this point represents 100% investment in stocks. This overall graph or curve is called the minimum variance frontier. It shows the minimum variance. It shows the minimum variance that can be achieved for a given level of expected return. So at any expected return, so let's take the 10% mark, this graph shows you the minimum variance. So this is a term that should be familiar. Next, point A, which is this point over here, represents the global minimum variance portfolio. So of all portfolios possible, this portfolio, portfolio A, has the lowest variance, and therefore it is called the global minimum variance portfolio. Then the third term that you need to learn here is the efficient frontier. So when we talk about the efficient frontier, it is all the portfolios on the minimum variance frontier that start at A and are above. So remember, so this part is called the efficient frontier, at and above A. Portion of the minimum variance frontier beginning with the global minimum variance portfolio and continuing above it, it shows the highest expected return for a given level of risk. So this is the efficient frontier. All right, minimum variance frontier for different correlations. What we are showing here is the following. Let's say that this is our total investment in government bonds, so 100% invested in government bonds, and this is 100% investment in stocks. This dashed line shows us the return and risk characteristics of a portfolio if the correlation between stocks and bonds is equal to 1. With this dashed line, notice that there is no diversification benefit. You get a higher return only if you take on more risk. As the correlation coefficient starts decreasing, then there is a diversification benefit. So if we take this particular solid line or solid curve, here the correlation is equal to 0.5. This is the scenario that we just saw. We do have some diversification benefit in the sense that notice that as you start with government bonds and you start adding stocks, initially at a slightly lower risk, you can actually get a higher return. As the correlation coefficient decreases, so this dotted line now shows a correlation coefficient of 0. In other words, there is no correlation between the two asset classes. Then what happens? Then you have even more of a diversification benefit where you can get to a point like this where you have substantially reduced the risk and you are getting a much better return relative to this point. If we take this to an extreme, the greatest diversification benefit can be realized if the correlation is -1, and that is shown over here. So this represents the risk return characteristics if we have a correlation coefficient of -1. And we can actually come up with a portfolio with a return that is higher than the return on the bonds at 0 risk. But unfortunately, a correlation of -1 is a theoretical number. It is very hard or almost impossible to find this in practice. At level 3, we will go through exercises where we try to figure out this expected return. It is a fairly straightforward calculation. The key takeaway from this discussion is that as the correlation decreases, the diversification benefit increases. Okay, we talked about the 2-asset case. Now we move to a 3-asset case. Personally, I think that the probability of this showing up on the exam is low, but we are covering this because it is mentioned in the learning objectives. So you need to learn the formulas. And I believe that once you understand the format and the flow, then this is also fairly easy to remember. The expected return of the portfolio is simply the weighted average. So that is not a problem. And if you think about the variance of the portfolio, it is just an extension of what you saw in the 2-asset case. These two numbers come straight from the 2-asset scenario. And if you have a third asset, then it only makes sense that you have W3 squared, sigma 3 squared. If you have a third asset, then it only makes sense that you have W3 squared, sigma 3 squared. And then recognize that if you have 3 assets, 1, 2, and 3, then there will be 3 pairwise correlations. Hopefully you also recognize if you have 3 assets, then there will be 3 pairwise correlations, a correlation between 1 and 3, between 2 and 3, and between 1 and 2. And hopefully you recognize that the correlation between 1 and 2 is the same thing as saying the correlation between 2 and 1. So we'll just keep this format. Then the remaining 3 terms are anchored around each of those 3 correlations, and the rest of the terms should be familiar from the 2-asset case. So if you keep this in mind, then the formula for the 3-asset case is simple. All right, we don't need to do this, but mechanically and mathematically you can see that with different possible weightages of the 3 assets, you can come up with expected return, variance, and standard deviation. Comparing minimum variance frontiers, the 3-asset versus 2-asset scenario. Here we'll make a very straightforward point. If we look at this dotted line, this is the minimum variance frontier for the 2-asset case. Now that we add the 3rd asset, we get a new minimum variance frontier which dominates the 2-asset case. And what does it mean when I say that it dominates? All I mean is that for a given level of risk, the expected return now is higher with the 3-asset case, or putting it another way, at a given level of return, the risk is low. So clearly adding that 3rd asset helped us. It made the efficient frontier even more efficient. All right, and these are phrases from the curriculum which I'll read out aloud so that they can be memorized. We generally can improve the risk-return trade-off by expanding the set of assets in which we invest. So when you add more assets, that improves your diversification. The second point is that the composition of the minimum variance portfolio for any particular level of expected return depends on the expected returns, the variances, and the correlations of those returns and the number of assets. So we've seen this. All right, so we've taken a 2-asset case, a 3-asset case. Now let's talk about the minimum variance frontier for many assets. I've taken some expressions from the curriculum, and you don't really need to get intimidated by these. You just need to understand what is going on. If you have many assets, 4 or more, let's say, the expected return on the portfolio is straightforward. It is simply a weighted average of the expected return of every asset in the portfolio. So this is straightforward. The variance of the portfolio is a little more complicated. I don't think you really need to memorize this expression, but understand this basic concept. The variance will depend on the weightages. It will depend on the variance of each asset, and it will depend on the covariance or the correlation of each asset. In other words, it depends on the pairwise covariances of all the assets in the portfolio. And this is a mathematical way of expressing that. So how do we come up with a minimum variance frontier given many assets? So this is our minimum variance frontier. Essentially, we ask the computer to do this exercise. So in simple terms, what do we tell the computer? We tell the computer that, look, we have all these assets, and one constraint is that the sum of the weightages of all the assets can only be 1. Okay, because otherwise it would not make sense. So the sum of the weightages is 1. That is one constraint. Then the other constraint you give to the computer is that for each level of return, give me the lowest possible variance. And essentially, if you think about it, the computer's job is to find the weightages. So find the relevant weightage of every asset in my portfolio such that at a given level of return, say 12%, my variance is minimized. If we do that for every return, so for every level of expected return, the computer is giving us the weightages such that the variance is minimized, and then it is giving us that minimum variance. What can we plot out? We then essentially have the minimum variance frontier. These are the various symbols and mathematical expressions used in the curriculum, but as long as you understand the concept that I explained, you should be in good shape. All right, just for illustration, here is the minimum variance frontier for 4 asset classes given data from 1970 to 2002. And what does this show? If you look at this square over here, this represents the S&P 500. What you are looking at here is that there is a portfolio on the efficient frontier that dominates 100% investment in the S&P 500. So there is some portfolio, some combination of your 4 assets such that at the same risk as the S&P 500, so S&P 500 during this time had a risk of 15%. At the same risk, you can create another portfolio with a certain weightage of the 4 asset classes that your return is higher. If you put all your money in ex-US, which means non-US stocks, then your return would be here, but there is an efficient portfolio that dominates. Now, you don't need to calculate or come up with this. You just need to know the process that I just talked about and recognize the fact that this happens in a computer. All right. Diversification and portfolio size. Now, here are 2 important questions. How many different stocks must we hold in order to have a well-diversified portfolio? Based on what I've said so far, it seems like as we keep adding more stocks, the diversification benefit improves. But then does that mean that we should have an infinite number of stocks? Probably not. I think just intuitively you can recognize that as you keep adding more stocks, the marginal benefit decreases. Okay, so just keep that at the back of your mind. How does covariance or correlation interact with portfolio size in determining a portfolio's risk? At a high level, we've said that if the correlation is low, then the diversification benefit is good. So lower the correlation, higher the diversification benefit. But let's try and quantify that. All right. I'm going to show you 2 formulas and then emphasize one of those. Suppose we purchase a portfolio of N stocks and put an equal fraction of the value of the portfolio into each of the stocks. Sometimes this long phrase will be expressed as an equal weighted portfolio. It can be shown that the variance of returns for the overall portfolio equal this expression. And you need to understand all the terms over here. What does N mean? It is the number of stocks in your portfolio. What does this term mean? Sigma bar squared. This is the average variance of all the stocks in your portfolio. So just to highlight the fact here, say in your portfolio you have 6 stocks. Can every stock have a different variance? Yes, in this particular scenario, we are saying that that is possible. Stock 1 will have a variance of sigma 1 squared, stock 6 will have a variance of sigma 6 squared, and so on. So what we do here is take the average variance plus n minus 1 over n times the average covariance. So there will be several pairwise covariances. We take all those covariances and find the average. That is this number. All right, so this is one formula. What do you think happens to this formula as n becomes very large? So as n starts moving towards infinity, what happens to this expression? Notice that this cancels out if n becomes very large, and this becomes essentially 1. So then the variance of the portfolio simply becomes equal to the average covariance. All right, so this is one fact. You don't really need to know the derivation of this formula, just need to know the formula. And in fact, there is another formula that I will emphasize because that's the one that you need to learn. That's the one that has questions based on it at the end of the chapter. Okay, if we make some more simplifying assumptions, and those simplifying assumptions are shown here. Equal weight, so that actually is an assumption that we are carrying forward. If you have $100 to invest in 100 stocks, you put $1 in each stock. So your portfolio needs to be equal weighted. All stocks should have the same variance. You make an assumption here, and this is a simplification, that all stocks in your portfolio have the same variance. And then you also make an assumption that all stocks have the same pairwise correlation. If we make these three simplifying assumptions, then we get a simpler expression. This is the new expression for the variance of the portfolio. And I'll emphasize that this is the expression that you need to memorize. The derivation is given in the curriculum, but you don't need to know that. I'll just help you basically understand the intuition behind this. First, understand what you are looking at. What is this sigma squared? This is the variance of the stocks, and we've said that all stocks have the same variance in our simplified model. What is this? This is the correlation, and again we have made a simplifying assumption that the correlations are the same. All right. Now think about it. As n increases, what do you think should happen to the variance of the portfolio? It should come down. That's why n is in the denominator. What should be your basis for the variance of the portfolio? The basis or the starting point can be sigma squared. So the average variance is your starting point, and then there will be a factor. So this factor is going to be less than 1, because clearly the variance of the portfolio is going to be less than the variance of each stock in the portfolio. Now what happens to this expression if n becomes large? If n becomes large, then this becomes close to 0. And what are we left with? We are left with the variance of the portfolio is equal to the variance of your stocks in the portfolio times the correlation. And this should also make intuitive sense. If the correlation is low, then the variance of the portfolio will be much lower than the variance of each stock in the portfolio. Now I will pause over here. I want you to stare at this formula and memorize it. Okay, so hopefully this is memorized. Now I want you to do these questions. Here is the formula that I asked you to memorize, and this is what we are using. Just plug in the numbers for the first scenario and you will get a variance of 365.4, and then the standard deviation is simply the square root. With 24 stocks, the standard deviation is higher, which makes sense. You have fewer stocks. So initially we had 100. Now we have 24, and the standard deviation went up. But notice that the number of stocks came down a lot, from 100 down to 24, but the standard deviation only went up marginally. All right. Now if we go to the other extreme, where we have an infinite number of stocks, then the standard deviation, or then the variance, is based on this formula that we talked about on the previous slide. So the variance is 360 and the standard deviation is approximately 19. So look at the difference between a 24 stock portfolio and a portfolio with an infinite number of stocks. The difference in the standard deviation is only 0.6. So it is only a marginal difference. And what this illustrates is that with approximately 20 to 25 stocks, you can get almost the same level of diversification benefit that you get with a much larger number of stocks. So that is what is being illustrated over here. The larger part of your diversification benefit then really comes from the correlation. So notice if this correlation goes from 0.4 down to 0.3, then that will have a significant impact on your risk of the portfolio. Coming now to section 2.5, portfolio choice with a risk-free asset. And most of this material should look familiar. We'll talk here about the capital allocation line. The capital allocation line, or CAL, describes the combinations of expected return and standard deviation of return available to an investor from combining her optimal portfolio of risky assets with the risk-free asset. So what is going on here? Based on the earlier segments, we came up with this minimum variance frontier. So that is, let's say, this curve over here. The constraint that we had so far was that we can only invest in risky assets. Therefore, we did not have any portfolio with a risk of 0. So there was nothing to the left of that global minimum variance. But now we have relaxed the constraint, and now we are saying that we can also have a risk-free asset in our portfolio. Let's say that the risk-free asset is your T-bill with a return of 4%. So this point then reflects the return of 4% at a risk of 0. The risk is being measured in terms of the standard deviation of returns of the portfolio, so denoted by sigma p. All right. Now, if you combine your risk-free asset with a portfolio, let's say you take this portfolio over here, call this portfolio X. Can you combine the risk-free asset with X? The answer is you can. And then if you create a line from 4% to X, this line represents various combinations of portfolio X and the risk-free asset. But can we do better than X? The answer is yes. The best we can do is by combining the risk-free asset with this portfolio here, which is called portfolio T, or the tangency portfolio. This is the optimal risky portfolio. And why do we call this the optimal risky portfolio? Because for a given amount of risk, this tangency line will give us the highest additional return. You think about it, this has the highest possible slope. It clearly has a higher slope than this previous line that I drew. If you say, what about a line like this? It does have a higher slope, but we cannot find portfolios over here. So the efficient frontier is sort of a frontier or a bound on the best we can do. So this line then is called the capital allocation line. In a sense, it is the new efficient frontier as long as you can invest in the risk-free asset. All right. Now, what is the formula of the capital allocation line? This calculation is fairly straightforward. Here is what we are going to do. We are using the form Y, which is expected return, is equal to mx plus c. So y is the expected return, m is the slope, and c is the y-axis intercept. So the y becomes the expected return on the portfolio. The c becomes the risk-free rate. So this is your risk-free rate. The x is our risk. So the x is the risk of the portfolio. So the only thing that we have to calculate then is the slope. The slope is the change in y over change in x. What is the change in y? So what is this distance? This distance is the expected return on the tangency portfolio minus the risk-free rate. So that's the numerator. What is the denominator? The denominator is the risk of the tangency portfolio. So that's this point. And this then is our slope. And this slope is also the Sharpe ratio of the tangency portfolio. And since the slope is the Sharpe ratio of the tangency portfolio, and we've shown that this particular line has the highest Sharpe ratio, then again it makes sense that this is the best we can do. So if you recall, what was the Sharpe ratio? It was the return on a given portfolio minus the risk-free rate divided by the risk or standard deviation of that portfolio. Using the terminology from the curriculum, the T simply stands for the tangency portfolio. So you replace the P with T. Okay, so this is one point. What about the expected returns and the risk at any given point on this line, on the cal? Okay, so let's work through a simple scenario. The expected return at any given point is simply the weighted average of the return of the tangency portfolio and the risk-free asset. So if your risk-free asset has a return of 4% and your tangency portfolio has a return of, let's say, 10%, then what is the return of a portfolio that is 50% here and 50% here? It would simply be 7%. As you add more of the tangency portfolio, then the expected return of the combined portfolio will be higher. So that is fairly straightforward. What about the risk? So let's go back to our formula for the risk of a portfolio. Let's take this particular scenario where we have 50% in the risk-free and 50% in the tangency portfolio. Our formula for the variance of the portfolio was this. It was W1 squared sigma 1 squared plus W2 squared sigma 2 squared plus 2 into various items, one of which was the correlation, and also here we had the risk of each item. So in fact, I'll put the whole formula down. So it was 2 into this into sigma 1, and you also have sigma 2, and you have W1 and W2. But we don't really need all these. Why? Because A, you know the correlation is 0. The correlation of any asset with the risk-free asset is 0, because the risk-free asset by definition does not have any variance regardless of what is happening to the other asset. So A, you know this is 0. You also know that the variance of the risk-free asset is 0. So clearly this term is 0. Now, since let's say that sigma 1, so 1 is our risk-free asset and 2 is our tangency portfolio, we know that this is also 0. So that cancels out. So the variance of the overall portfolio, which is a combination of our risk-free asset and the tangency portfolio, is simply equal to the weight of the tangency portfolio, which in my example is 50%. So weight squared into the variance of the tangency portfolio. And then you can take the square root and you can say that the standard deviation of the portfolio is simply the weight of the tangency portfolio into the standard deviation of the tangency portfolio. Now, if the standard deviation of the tangency portfolio is 20%, and you create this portfolio over here that is 50% invested in the risk-free asset and 50% in the tangency portfolio, then what is the risk of that particular portfolio? Call this P. It is simply the weight times the risk of the tangency portfolio, which I said is 20%. So this is going to be 10%. It's a fairly straightforward calculation. Once you've understood this concept, then you can just remember the fact shown right here. Now I want you to work through example 5. So here is what you do. First thing I suggest is you simply draw the picture. So this is showing the risk-free asset 5%. The tangency portfolio has a return of 15% and a risk of 25%. We don't really need to create the efficient frontier over here. Question 1 is, how much return does this investor demand in order to take an extra unit of risk? So what we are doing here is coming up with the slope of this line, which is the Sharpe ratio, and that is 15 minus 5 divided by 25. The answer is 0.4. Next question is that the investor wants a portfolio standard deviation of 10%. What percent should be invested in the tangency portfolio? So this is the formula that you need to use. We saw this on the previous slide. Sigma P is 0.1, that's given. 10% needs to be expressed as a decimal. WT is what we need to find, and 0.25 is the risk of the tangency portfolio. You do the calculation and you get a weight of 0.4, which is 40%. We also need to find the expected return. So how do we do that? Take the weighted average here. 60% is going into the risk-free asset. So 0.6 into 5% plus 0.4 into 15, that is 9%. Now do part 3. So part 3 is simple. The return is simply the weighted average. The risk is 0.6 into 0.25. The mistake that some people might make is to plug in 40%, but keep in mind that in this formula, it is the weight of the tangency portfolio that we need, and that weight is 60% or 0.6. Now do the remaining 3. So for part 4, notice that we are considering a portfolio that has more risk than the tangency portfolio. And this happens by borrowing at the risk-free rate. The simplest way to solve this is to use the CML formula that we have derived. The return on the portfolio is equal to the risk-free rate, and here we should use all decimals. So 5% means 0.05 plus 0.4 is the slope, which we've already calculated before, times the x-axis value, which is the risk, and this is given in part 4, 0.35. You do the calculations and you get 0.19, which means 19%. So here is how you do this. The return for our portfolio is 19%, that's this number. This has to be 1 minus WT, which is the weight in the risk-free asset, times the return on the risk-free asset, plus the weight of the tangency portfolio into the return of the tangency portfolio. You solve for WT and you get 1.4. So at this point, you have a weightage in the tangency portfolio of 1.4. But the sum of the weights has to be 1. Therefore, the weight in the risk-free asset must be equal to minus 0.4. The interpretation of the minus is that instead of investing, you are borrowing at the risk-free rate. So you borrow at the risk-free rate, invest in the tangency portfolio, and that gives you a return of 19%, but at the higher risk of 35%. Now let's do 6. So this is fairly straightforward given what we've talked about. This is the amount available to invest. The borrowing will have to be based on this factor. So borrow 4 million and make a total investment then of 14 million. So this is a leveraged investment. You might recall from level 1 that before this point, we call this the lending part, because here we are lending to the government, and this is the borrowing part, because here we are borrowing at the risk-free rate.